Okay, I think we'll get started. If you're coming here from the GNL project, I encourage you to look at the introductory video to this series to make sure this is the right course for you. We're going to pick up with energy again, and we're talking about conservation of energy. We've already started to see all the good consequences of that. We did the LEAP problem last lecture. You're starting to do a lot of these problems in your homework. So you're seeing the benefit of conservation of energy. Well, let's sort of put it all together, and then let's look at these things called energy diagrams to get a sense of what the system is going to do. That's going to be our main focus for today. Okay, so just a couple of things that we've kind of said along the way. Conservation of energy through Nodier's theorem is connected to a deep symmetry of nature, and that is time symmetry. So very loosely speaking, the physics of today is the same as the physics of tomorrow, is the same as physics of yesterday. Of course, this is a much more sophisticated mathematical theorem than that, but this idea that every symmetry of nature has a conservation law, and every conservation law has a symmetry. We have two types of systems: conservative systems. This is where you can think of the particle completely, or the object completely isolated from the rest of the universe, in which case conservation of energy, which says delta E is 0, also says that delta E is equal to any change in kinetic or potential energy. And so from this is where we got delta U equals minus delta K for conservative systems. Then we ended last time talking about thermal energy and heat. So this would be non-conservative systems that interact with their environment. That can be interaction through drag, by moving through the air, or by friction. Again, conservation of energy says overall the energy is 0, but now we have to include change in kinetic energy, change in potential energy, and then minus any heat that was lost to the environment. We saw, as I mentioned in the beginning of this video, we saw an example last time of the LEAP problem, which was a relatively difficult problem for us right at the beginning of the course, and now it's almost trivial with using this. And a lot of the homework that you've been doing has been showing that. Okay, let's kind of put this all this together diagrammatically, and we'll draw what we call energy diagrams. And so the spring formula for energy is 1/2 K, and this is little k, this is the spring constant K, not kinetic energy K, times the displacement of that spring from the equilibrium position. And so if we notice this is a parabola. So let's sketch that parabola on an energy. This is energy over here. This is displacement over here. And let's sketch this parabola. So this parabola here, that's this curve. And then we know that energy is conserved. So this is E total, and that's a constant throughout. So no matter how much we pull or stretch that spring, the energy is conserved. So this will be a certain amount of energy that we've dumped into this spring mass system. And let's see what happens. Well, we have the spring mass. Let's put some energy in, maybe with an impulse or something. So we've added a certain amount of energy. And we could think of that in two ways. We could think about that as, or in many ways, we could pull the spring back. So we've introduced some potential energy, then we're going to just let it go. Or we could have it sitting still and hit it with a hammer and introduce some kinetic energy. Either way, we've introduced some total amount of energy into the system, and that's illustrated by this line. Now, where this line intersects the parabola by just what graphs mean, that says that U equals E. So U equals E at both of these points. Those positions here on the x coordinate, or the displacement coordinate, are called the turning points. So as this spring mass system goes back and forth, it'll be where it turns around here, and where it turns around here is when the kinetic energy, or when the potential energy is equal to the total energy. Everywhere in between, then the kinetic energy is given to us. Potential energy is given to us by the curve, and the kinetic energy is given to us from the curve up to the total energy. And so here we can see everywhere along here, we can see the change of potential energy going into kinetic energy. And it's right here at this equilibrium point where the kinetic energy and the total energy are the same. Then we speed past this, we start to lose kinetic energy and pick up some potential energy, and we hit the other turning point where we've converted all the way. Okay, so this is called an energy diagram, and it captures in this the motion of the system. So you want to be able to look at this diagram and see it going from side to side as it's gaining and losing potential energy, gaining and losing kinetic energy, such that the potential energy plus the kinetic energy is always equal to E. Okay, well, let's do a different one. Let's do gravity. So here we might imagine a perfect super ball where we drop it, we bring it to a height h, drop it, it's going to hit the ground, come back to height h, hit the ground, come back to height h, hit the ground, come back to height h, forever. So let's look at this case, and we are going to imagine here now we've raised it up to a certain amount and given it a total energy E. So that's going to be a constant throughout, and then we'll plot this potential energy. It's linear with height, and so as we let it go, it'll head to the floor. It'll pick up some kinetic energy. This will be the potential energy. It'll hit the floor down here where the kinetic energy is equal to the total energy. And then here is where the potential energy is equal to the total energy. And everywhere in between, some kinetic, some potential energy. The turning point is right here again where those two cross. Okay. Let's look now at this idea of equilibrium and stability. So let's imagine we've got some just crazy curve representing the energy landscape, as it's called, of the system. And we identify some special points here. This point is called a local minimum because if I go a little bit in either direction, my potential energy rises, but I can find another spot where it's actually lower. And that spot is called a global minimum because it's a minimum if I go in any direction. In fact, if I go anywhere on the graph, I'm higher than that. And so that's the global minimum. Both global minima and local minima are stable situations. That is, if we kick the system with a little bit of energy, just based like over here, we'll see it go back and forth, but it'll stay local to that minimum. Same thing over here. Now, here's another type of point. Here's a maximum, a local maximum. This is unstable because if we kick this with a little bit of energy in a given direction, it'll just take off in either of these directions and go back and forth. So if we just raise that energy just a little bit, so here it's just sitting still, we raise it just a little bit, it'll go back and forth a long ways from that local position. So that's local max and local min. Okay, I want to go through what about a dissipative system. So these are all been conservative systems. So I'm going to erase this and redraw the spring, but for a dissipative system. So let's imagine that spring, well, even a real spring. Let's imagine a real spring. We let it go. It's going to oscillate for a long, long time, but because it's in air, there's some drag, and every time it comes back, it doesn't quite come all the way back. So let's try to reflect that in a graph like this. So I'll make my energy versus displacement here. There's my parabola. And I'm going to start here now with a certain, let's imagine I pull it back and I'm going to let it go. Now, let me sketch in the energy for the conservative system. Right? If there was no drag, then this would just keep going back and forth like this. But because there's some drag, by the time it gets over here, it will be a little bit, it'll hit this a little sooner. So if this is the turning point right here, it's actually going to turn right here. That will be the real turning point. So this is the real turning point. and this would be the conservative turning point. And likewise, back here, it'll be a little less. So again, we would come down. So our path would look like this. We might oscillate many, many, many times, but eventually we would end up right down at a stopped spring. So we know that if we were to go into the lab, the physics lab, let a spring go, it'll go and go and go and go, but eventually if we were to come back later, it'll be stopped. And that's what's happening here. So these diagrams extend to dissipative systems as well. So keep telling yourself the story of this. It's less easy to have problems like this, so you won't see any in the problem sets from the book. But this is really important ideas in terms of internalizing and understanding the nature of energy in systems and how conservative versus dissipative systems behave.